Next week we have off from quizzes, so that's a nice break. And then also next lecture is a hard pivot away from what we're doing now. It's completely different material from what we're going to do today. Also, the content that I'm going to go over today is not on a quiz. So you will see it on the final, but your next quiz will be on the new material that we start in lecture next week, and then you'll start it, I think, in DL8, which you should see at the end of this week or beginning of next. So last week we left off talking about just general linear transport, which is just the model, the general model we've been using to talk about both fluids and electrical circuits, where we have some gradient. Usually it's an energy density, like energy per volume or energy per charge, that we have a high and a low, so that's the gradient, just like a difference between 2 points. Some resistance in between those points, and depending on what that delta phi, the gradient, and what the resistance are, you get some flow rate, right? And the bigger the difference, the greater the flow rate. Bigger the resistance, smaller the flow rate. And with steady state systems, that's kind of it. We just look at the difference between different points in the system, and those differences don't change over time. However, as we kind of hinted about last lecture, and I think you've seen by now in DL, that these differences are not always constant. So delta phi can change over time when we would get non-steady state. And we won't do this too quantitatively, but I think a good just general example is heat flow, where we have something that's hot, something that's cold, separated by an insulator, a resistor, and as heat flows from hot to cold, the hot becomes colder and the cold becomes hotter until they reach a temperature in the middle, somewhere in between, and they're at equilibrium, and heat flow will stop. So here's our little flow equation here. P is just our flow rate. It's P because the flow of heat is power. But the higher the power or the flow rate is proportional to delta T, so the difference in temperature. So when we have the maximum difference, hot and cold, the flow rate is the highest it will ever be. And then as those two temperatures come toward each other, delta T shrinks, the difference in temperature, and as a result, the flow rate also shrinks. So if I have a cooler on a hot day, it will go from cold, like really cold, to room temperature relatively quickly when the delta T is big. It's hot outside, cold in the cooler. But once the cooler's room temperature and maybe outside is hot, there's still a temperature difference, so the cooler's still going to keep heating up until it gets to the temperature of the air, but that will be a lot slower than it getting from cold to room temp, right? So it changes very quickly at first, and then as the delta T shrinks, it changes less quickly. So connecting this to fluids, which you've seen in DL by this point, right? You did an experiment that looks just like this, right? Where you graph, or you just observe the fluid flowing from one to the other through this little tube in the bottom right, and you notice that it changes really quickly at first and slowly later on. You did do this, right? Yeah? Okay, so I think this is the better example. You'd also, maybe if you had time for it, there's like a diffusion example where there's like water flowing into a little dye packet. That experiment is kind of awful, but you don't need to worry about it. This is a much more helpful example. We have two heights, right? They start different. That's the maximum difference they'll ever have. And then as water flows down through this resisting pipe in the middle from one side into the other, the heights equalize, right? And they eventually reach the same height, at which point our current becomes zero. So both the height difference and the current are going from some maximum value down to zero. So let's try applying Bernoulli's equation to these. So I know we've talked about Bernoulli's equation, and our big asterisk was that it was always in steady state. And now these are clearly not steady state systems. Like this isn't a steady state system because it's changing from one time to another. However, you can still use that equation at individual snapshots, right? So if I just take this frozen example on the left, I can apply Bernoulli's equation, same on the right. I just need two separate ones, right? So let's do that. On the left-hand side, Bernoulli's equation, we get delta P plus our rho G delta H. There is a height difference equals minus IR. I guess I should mention our start and end points are just the tops of the fluid in each column, right? So I'm going from the top of one down across the resistive pipe in the middle and up to the top of the other, which means what's our delta P? Well, if both are open to the atmosphere, there is no pressure difference. And so our Bernoulli's equation at this point is really simple. It's just rho g delta H equals minus IR. And we get what we expected. The higher the height difference, the more current we get, right? So we start out with this maximum delta H. As water flows from one side to the other, delta H shrinks. And if delta H goes down, you can see from this equation, I must go down as well. So now, if we were to take that all the way to our final point here, when the water levels are equal, delta P is still 0, right, because they're both at atmospheric pressure still. And now our delta H is 0 as well. So, I mean, this equation just kind of goes away. I equals 0 as well. There's no flow, which makes sense, right? There's no height difference. There's no water's not moving anywhere. This is perfectly in equilibrium. So, again, both delta H and current went from some maximum value down to 0. So just as a little, I'm not going to open a clicker question for this, but looking at these two systems, which one of these will have a larger current, a larger I? Left, raise your hand if you think it'll be the left. Yeah, and that's the answer. It is the one on the left. Why? Because we found that the flow rate, well, this is just Bernoulli's equation, and it tells us that the flow rate times R is equal to rho g delta H. In other words, flow rate is proportional to the height difference. So since the height difference in the one on the left is a lot bigger, we're going to get a larger flow rate. It's pretty intuitive. Okay, so now let's flip this around, something very similar, but not quite the same. And what I mean by that, so now we're going to start with equal water levels, but I'm going to put a pump in the middle. So now we're forcing water to have this delta H, right? Starting with delta H equals 0. The pump is what causes this energy density difference. And so the water levels will split. And the reason we're doing this is because this is more analogous to the electrical circuit that our goal is to analyze. So now water's flowing from right to left, and the water levels are becoming more and more different. And eventually, they're going to reach some maximum, and current is going to go to 0. And to see why that is, I mean, maybe it's just like intuitive that it just like won't just flow up forever. And we can see why with the Bernoulli equation. So now we've introduced an E pump term into here. So our starting case now, delta P is still 0 because they're both open to the atmosphere. Except now our starting delta H is also 0, right? The heights are equal. So our Bernoulli equation is just E pump over volume equals IR. So in other words, the flow rate is determined by the energy density of the pump, right? This, if you can kind of stretch a little bit, looks a lot like just a battery and a resistor in a circuit, right? Where the flow rate is determined by the strength of the battery, which is E pump over volume here, and the resistance R. And then what happens as water flows from left to right is that rho GH term becomes non-zero, right? As soon as water starts to flow, we have to uncross out the rho g delta H, and we do a little like analysis of what's growing and shrinking here. If before just E pump equals minus IR, so that means E pump minus IR equals 0, or sorry, E pump equals IR. If delta H increases, so that if this left-hand side, rho GH, becomes bigger, this IR term will have to grow in order for the equation to will have to shrink in order for that equation to work out. So let me say that again. As this height difference appears, we have to spend energy on this potential difference. And so we have less to spend on the thermal energy density, the minus IR term, if that makes sense. So just to make this equation work out, as delta H increases and the height difference grows, the current decreases. Another way to think of this is just the pump only has a certain amount of energy density to give, right? And once we spend all of that on potential energy going up on the other side of the tube, right, on the left-hand side as the water level grows, once that potential energy density is equal to the energy density of the pump, there will be no more flow. There will be no more energy density to spend, and so it will stop. So what we find is water level rises, and eventually potential energy density cancels out the energy density of the pump. So two things we know are that the flow rate depends on delta H, And that's kind of twofold. One, we just saw it with like Bernoulli's equation, right? As the height difference grows, that means we have less energy to spend on like thermal energy density, sure, and so the flow rate has to go down. But another way to see that is how are delta H and I related? Well, there's another way that they're related, not just from Bernoulli's equation. What is flow rate? It's like the flow of fluid over time, right? It's volume per second. And what determines the height, delta H, of the water in the two columns? The volume of fluid in them, right? If I displace some volume of fluid from the left to the right, then their heights will change accordingly. The left will shrink and the right will grow. I guess here it's the opposite, where I'm displacing water from the right to the left, and so the height on the left shrinks and the height on the right grows. And so H and I are related that way as well. The flow rate causes the change in height, if that makes sense. As fluid flows over time, the height grows. We need a factor of like pi r squared, because it's a cylinder, right? So to actually calculate the volume and relate it to the height, you need to do a little geometry. That I think you do in DL, but we're not going to be assessed on that. But anyway, I hope you can see that the larger the flow rate, or the flow rate determines the rate of change of the height, is I guess what I'm trying to say. In that the larger the flow rate, the larger the amount of volume per time flowing from one side to the other, the quicker delta H is going to change. And so we find that doubly, H and I are related. And the way they're related is that as delta H increases, I decreases. Right? So as the height difference increases, the flow rate, the current, goes down. And then also, as I decreases, H increases more slowly. So order of operations one more time. We have, looking at height difference, that is obviously increasing over time. We're pumping water from one side to the other. Height difference is growing. As a result of that height difference growing, the current is going to go down. And then as a result of the current going down, the speed at which the height is changing slows. So what we find is, at first, the height changes quickly, and they quickly reach some offset, and then as they get further and further apart, they're still growing. Delta H is still growing, but at a slower and slower rate until it reaches that maximum, where current is 0, so delta H is not changing anymore. The rate of change is 0, and they're at equilibrium. So put another way, larger delta H gives us smaller I, gives us a smaller rate of change of H, or delta H over delta T. This is like leaning toward calculus, which we're not really going to, you're not responsible for any calculus in this class, but it's like a derivative, a rate of change. It's just rise over run is what we're looking at. So getting rid of this middle step, or not getting rid of, but ignoring it for now, what we're finding is that the value of H, so the larger H, the growth of H, affects the rate of change of H. Right? So if I tell you just what the height difference is, that tells you something about how quickly the height difference is changing. And the same thing is true for the current. If I tell you what the current is, that tells you something about how quickly the current is changing. And the way we describe this type of thing is with exponentials. And I'll walk through why that is. So now I'm just going to talk about the pure math of it in general terms before we go back to how we're going to apply it. I'm going to speed through this, so if the exponential stuff doesn't sink in or you don't quite remember it, I'm sure we've all seen it in the past. I, of course, ask your TAs and me and office hours and stuff, but a quick YouTube video, just watching, I'm sure people have done it with great colors and plots and stuff like that. Just seeing someone work with exponentials could help refresh you. So anyway, the general expression for exponential decay meaning it's e to the negative something, is just our value, the thing that is decaying, y, as a function of time, is equal to some initial value, y naught, times e to the negative t over tau. So t is our time, that's our independent variable that just varies. Time goes from 0 to whatever time, and tau in y naught, our initial y, are some constants. So let's just plug some things in and see how we get this graph. If we plug in time equals 0, so our initial time, we get y naught times e to the negative 0. right? 0 over tau is just 0. So e to the 0 is 1, and we just get our initial value, y naught. So that's why we call it y naught, because it is our value of y at our initial time. And that's our maximum value that we start with. Then we plug in a bigger time. Let's just plug in whatever this tau is. So tau is just a constant. It's a number with units of seconds. And so if I plug in t equals tau, then I get y naught times e to the negative tau over tau, or e to the negative 1, which is just 1 over e. So plugging in tau, y of tau, so like the value of y after tau seconds is y naught over e, which is roughly a third of what its original value was. So that's telling us that we start at y naught, and then after some time equal to tau has elapsed, we've quickly decayed away to just about a third of our original value, really 1 over e of our original value. Then let's plug in some huge time, so a time much, much greater than whatever tau is. Then we get e to the negative really huge value, which is 1 over e to the really huge value, which is essentially 0. If you plug in a huge number for t, you get 0. And that's why we see this asymptotic curve along here. So after some time that's much greater than tau, we decay away slowly to 0. Yeah? So tau is, right now, it's just some constant. It's just what we plug into the exponential that determines some scale. I'll talk about it a lot more, and if it's not clear, then you can ask again. But yeah, right now it's just some constant that determines like how this curve behaves. And we're just kind of experimenting with it. So anyway, the asymptote, by definition, will never cross the x-axis here. It just gets infinitely closer. We know that's not how things behave in real life. Like if we have this water example, at some point there's going to be the last water molecule that goes from one side to the other. And it's a discrete thing, but this is an extremely good approximation, right? We all know like how many water molecules, not exactly, but we know it's a whole lot that are in those two tubes. Whenever we're talking about charge, we're talking about so many an unbelievable amount of charges, such that this smooth approximation is pretty accurate. But that being said, it will never cross the axis. It just asymptotically reaches it. So now let's talk about the slope, like the whole reason, or like the way this fits the behavior we were just talking about. So early on, like roughly before whatever this time tau is, which again right now is just some constant, some value of time, before that we have very quick change, right? We decay away from our initial value super quickly. We have a steep slope, a large delta y over delta t, if you want to think of it that way, or at least a large magnitude because it's negative. And then as we move further on, far past t, it becomes less and less steep, right? The rate of change decreases until we're barely changing at all over time here. And then once we get to, this is just all 0. The rate of change is essentially 0. And so we find that we get this behavior that we just described with the water flow, right? Where it changes quickly at first, and then even though it's still changing, it's changing at a slower rate later on. So what tau does is give this kind of time scale for where do we start to go from steep to shallow? How quickly does the system behave? And for the water example, as you might guess, it relates to a bunch of different things. It relates to the resistance in the pipe, the density of the fluid, gravity, the area of those cylinders, but they're just all constants. It just has to do with the characteristics of the system. It's not dependent on time, right? It is just a constant, a time scale. And so tau acts as this kind of characteristic that we can use to roughly describe the qualitative behavior. Very quantitatively, it's a constant in our equation. However, if I tell you the time constant, which that's what it's called, tau is our time constant. If I tell you it's 1 second, that tells you that after 1 second, the system will decay away, whatever value we're looking at, will decay away to about 1/3 of its original value. So it will significantly change within 1 second. And then after a few times that, maybe 3 or 4 seconds, it will be at equilibrium, right? So it just gives us a rough idea of how long it takes. If I told you our time constant is an hour, then after a couple seconds, we know our system's not really going to have changed at all, and that we're going to have to wait an hour for this to decay to 1/3, and then 3 or 4 hours for it to get closer to equilibrium. right? So our time constant both acts as this number that we plug in, but also it does give us some information roughly about the characteristics of it, of the circuit, fluid or electric. The other thing I want to mention, like, why do we pick tau? Like, why this weird number? Why do we care about when it reaches 1 over e and not like something easy like 1/2 of its original value? Well, we do, and you'll calculate half-life, and I think that is what you did in DL, right? You calculated the half-life. Half-life's nice because we can all think like that. If our initial value is 40, I want to know how long it takes to get to 20, not 20 over 40 over e. However, it's very easy to find, like, it's very easy to recover y naught over e from this equation, right? I just plug in t equals tau, and then bam, I get y naught over e. If I wanted to find out when y equals y naught over 2, then the number I have to plug in is very ugly, and I have to like solve for it. Or you see it's like ln2 times something. It's not pretty. So the time constant is kind of this nice middle ground where it gives us something that we know about the system, and it's easy to find from our equation. So anyway, that's why we use tau and not the half-life a lot of the time. But tau is the time constant. And then also I've plotted here like roughly before tau, like earlier than tau, so this is t equals 0 to tau, we get pretty fast, relatively steep rate of change here, and then after tau is when we get shallower. So that is like qualitative, like it is just continuously changing. It's always getting less and less steep, but tau is a nice kind of break point between early and late times. So if we take our fluid flow scenario, so actually going back to connecting this to what we observed in a physical system, we have 3 snapshots where at first the heights are equal, and then they start to grow apart, and then they reach an equilibrium where they're the maximum distance apart they can be, and there's no more flow. So here I'm going to graph the flow rate, and it turns out that anything that's changing this does follow exponential decay. So that's kind of a cool thing about it. We might have to change the constants up, but they all follow the same exponential decay. Anyway, we start with our maximum current, I naught. We can actually solve that from the Bernoulli equation I wrote out, but we won't do that here. So we start at I naught. That would be time A. Then after some time, the heights differ a little bit, and we know that as the height grows, the current decreases, right? And so after some amount of time, roughly tau maybe, B, we see current has decayed to about 1/3 or 1 over e of what it originally was. And then time C is much later on, once we are pretty much at equilibrium and the height can't change anymore, and so current reaches 0. And so this equation does indeed, at least qualitatively, fit the behavior we wanted to describe. I'm not doing like all the solving for like what exactly I naught is and how to get tau from all these constants. 1, because you do a bit of that in DL, and 2, because your assessments on exponential change are only going to be on capacitors, which I'll talk about in a sec. But just so you're not worried, right now I'm just trying to get us the qualitative idea and how to work around with exponentials. Capacitors are really the meat of what you'll be tested on. Mm-hmm. Yeah, exactly. So now, well, yeah, in a way. So I'll ask a question that kind of leads toward that. Still looking at this scenario, but what if instead of plotting the current over time, what if I wanted to plot the height difference? Right, so now height difference does not do what we just saw. What we just saw started at some value and decayed away to 0. But what does height difference do? It starts at 0 and then grows to some maximum value, which is not that exponential decay that we just saw. It is a form of exponential decay, but this equation won't do it, right? Because we know that the form this equation takes is that downward sloping maximum down to asymptote with 0, which is wrong. So the thing that doesn't work out is that h increases over time. We want h to increase, whereas that decreases. But the thing that does still happen is that the rate of change of h decreases over time, right? So we still, in the graph we just saw for current, here, I'll pull it back up. We don't want this downward sloping, but we do want it to start steep and then get more shallow. Why? Because, I mean, we saw that with delta H, and we can see it just from current. If the current is getting slower, then the delta H also has to get slower because the current is the rate of change of delta H, right? So just the fact that the current is decreasing tells us that delta H has to slow down in its change. So anyway, we still want this type of curve, but we need it to increase. And so what does that look like? It looks like this. And so you can see in the top right here, the form is pretty similar, except now instead of h naught times e to the negative t over tau, we have h naught times 1 minus e to the negative t over tau. And that gives us this flipped graph here. And we still call this exponential decay because decay doesn't refer, at least the way we're using it, we're not using it to refer to the decay of like this value. So if I say the current is showing exponential decay, I'm not saying that the current, I mean it is, but I'm not saying that the current is decreasing to 0. I'm saying that the rate of change of the current is decreasing to 0. Similarly with height here, I could say this is exponential decay. Height is not decaying, right? Height is increasing, but the slope, the rate of change of the height, is decreasing, and it's reaching this maximum value at equilibrium, and it's going to stop there. So you could think of it as the behavior is decaying away. Yeah? They are related to each other, but not equal. So that'll be easier maybe to see with circuits when we start doing numbers. This lecture, I'm not going to do a ton of like algebraic manipulation. That's mostly left up for you in DL, and we'll give you like practice problems and stuff. But yeah, they're intimately related. Okay, so now we have the forms of our equation for like growth and decay. There's one more thing I wanted to say about them, blanking on it. But anyway, you still see same type of thing. After tau, we go from steep to shallower, right? At this point, now it's not decaying away to 1/3 of the value. It's actually reaching h naught times 1 minus e. So I don't know, or 1 minus 1 over e. So it's about it's how long it takes to get to about 2/3 of h naught. But still, tau acts as a characteristic time scale, where if I tell you it's a second, 1 second we'll get most of the way there, and then after a few more seconds we'll get to equilibrium. The other thing I wanted to say is that in general, whether we're increasing or decreasing, the behavior that we're going to see for all of these values that change exponentially is that we start away from equilibrium and then approach equilibrium exponentially, meaning we go quickly toward it, and then as we get closer and closer toward equilibrium, we approach it slower and slower. So that's the general theme here. So now let's actually pivot to something that you'll be tested on, like have to work with numerically, capacitors. And so I'll go through this in more detail, but just to give us a window into it, the setup is very similar, where we have this kind of reservoir on each side and then a pump in the middle, except now the reservoir is capacitor plates, and we're replacing the pump with a battery. But as we'll see, we get this similar behavior where we have a maximum current that decays away to 0 and some difference that's being created in between them. So is this exponential decay? And we'll find yes, because the battery drives this difference to grow. And as we get closer and closer to the maximum difference between the two plates, then the current will slow down. And we know that because just like the delta H and the current for the water were related, like the current causes the delta H to grow, same thing here, where our current causes this charge difference, which that's what this is. We're taking charge from one side and putting it on the other. If there's no current, then no more charge will flow. So those two things are related the same way. So anyway, it is exponential change where the behaviors will decay toward equilibrium. One of the ways we can see that, or one of the reasons that's true, is that like charges repel. So now I'm zooming in on just one of these plates, so just this right side here. And what it is really what I'm saying, just like a metal plate. So imagine just a disk of metal, neutrally charged, so it doesn't have extra positive charges or negatives. There's atoms on it with tons of electrons and protons, but the net charge is 0, right? And so now I'm going to put one excess positive charge on it. fine. There's no reason I can't do that, right? It's just taking a charge. Metal is a conductor, so it just slides right on down, lands on the plate. No issue. Now I'm going to do it again, and I'm going to put another charge on there. Except now, these charges are like charges, and so they repel. They don't want to be near each other. And so unless I force them onto there, they're going to want to spread apart as much as they can, and one of them is going to want to leave, at least. And then as I keep adding more and more charges, they spread out more and more. They want to spread out more and more, right? They're surrounded by like charges. They don't want to be there. And there's finite amount of space, right? So as I add more charges, there's less room for each of them on the plate, and so they just get forced together, and they really want to leave. So it becomes difficult to add more. Yeah. It is, yeah. So that's a good point. We know in real life, electrons are the thing that's flowing. So when you see a positive charge, we're going to think of things in terms of positive charges. It's just what's done, and it does make the math a little easier. But what's really happening is anytime you see a positive charge, that's a lack of an electron where there used to be one. Even though we'll talk about it as if it was the positive charges that are moving around. It's a good point. So anyway, as we add more and more charge, it becomes harder and harder to put more on. Just like with the fluid columns, as I add more and more water and H grows, it becomes harder and harder to put more water there because I have to cancel out this potential energy density. Here I have to cancel out this repulsive force. So as charge accumulates, the rate of change of I is going to decrease. As we pump charge around the circuit and put some charge on one side and opposite charge on the other, it becomes harder and harder to do so until we can't do it anymore. So the current goes from some positive value to 0 once the plates are full, which we'll see what that means. So we can describe this like difficulty. So far I've just been talking about it vaguely as like it's hard to put a charge on there with voltage. And as we pump charge from one plate to another, we get a voltage difference that builds up. That's our energy density, right? If you put a bunch of charges on a plate, that requires some energy density to do so, and that comes from the battery. So what happens like to create this setup that I have right here is that I'm just taking a positive charge from the left-hand side, moving it through the battery, and placing it on the right-hand side. So that's like our pumping, right? They start neutral, and then the battery's connected, and it starts to pump them up in opposite directions. One becomes more negative, the other becomes more positive. And the resulting voltage difference, so this is the voltage difference between these two plates, between the left and the right side, is related to the charge, Q, and the capacitance, which is like the characteristic value. Like a resistor has resistance, capacitor has capacitance, but it really is like the capacity of that capacitor, if you will. So these are both the same equation, just rearranged. Let's look at the one on the right. Delta VQ, the difference between the two plates, the difference in voltage between the two plates. If I increase Q, increase the charge, so put more charge on each plate, then my voltage difference grows, right? Because it's harder to do that. So the more charges I pack onto these plates, the more like charges I pack, the less they want to be there, the more they're forcing back, and so the more energy density difference there is. And then the capacitance works the other way. Capacitance, there's a bunch of things that change it, but one of the things is just making the capacitor bigger. So if I have this setup here, I have some amount of charge on these plates, some capacitance that they have is just a characteristic of them. Now I have some voltage difference. Then if I were to keep everything the same, keep the amount of charge on them the same, and make the capacitance twice as big, so in other words, just make the plates twice as big, now the charges can spread out, and they don't want to leave. They're not repelling each other as much because they have more space, and so the voltage difference between them shrinks, which we can see here. If I increase C, increase the capacity, then the voltage difference goes down, right? So the voltage difference ends up just being like basically a measure of how little the charges want to be there, right? If I either put way too much charge or don't give them a lot of space, I'll get a really big voltage difference. And if I have not a lot of charge or a ton of space for them to go, then I'll get a small voltage difference. Okay, so now let's see like the in-between, like how these actually get to equilibrium and what that looks like, which it turns out to be exponential decay. And we'll do that by using the loop rule. So now we've just developed the language we need to do that, or we found what the voltage difference across a capacitor is. So if you notice, the drawing's a bit different now. I just took the capacitor that I had before, and I took the plates and like smushed them together and added a resistor. But I just took these two plates and just put them together. There's two reasons for that. One, it allows us to draw it nicely and like kind of view it as an element in a circuit, right? So now like a loop is a little more obvious. But also, configuring them like this actually increases the capacitance a little bit. So like we're just going to like get some value C and use it here. Like this is just a drawing. But in real life, if you took a capacitor and arranged it like this, or arranged the plates like this, when they're close together, sure, the positive charges and the negative charges still don't want to be near each other. This negative charge doesn't want to be near this one or this one. However, now that these positive charges are over here, there's a little bit of attraction between the two plates, and so that makes it slightly easier to put more charge on. They still overwhelmingly would like to leave, and so there's still a voltage difference. However, putting them close together increases the capacitance a little bit. So that's another thing, that you can either increase the area of the plates or bring the plates closer together. There's a bunch of ways to increase capacitance, but increasing capacitance is essentially making it easier to put more charge on the plate. So anyway, now we've done that, and our capacitor is just like a piece of our circuit now. So if we do the loop rule, I'll go starting before the battery through it. So I pick up a plus epsilon, and then I come down here to my capacitor, and I know the voltage change across it is Q over C, right? So I just take however much charge is on it, divide by the capacitance, and that's my voltage change going across it. How do I get my negative sign here? Like, why do I know it's minus Q over C? Well, let's look at the way current flows, right? The flow of current is still determined by the battery, and we know that positive charges come out of the positive side of the battery. So if I take the positive side of the battery, which is on the right, they flow around clockwise and then hit this capacitor. And there's nowhere for them to go. They just build up on here. So what about the other side? Well, where do these positive charges come from? The battery doesn't make charge. It just pumps it around. And so that's why these negative charges are here. What's really happening is when we started from neutral, the battery removes a positive charge from this left plate, which creates a negative in its place, an excess negative. Then that charge flows around through the resistor, through the battery, and winds up on this other capacitor plate where it becomes an excess positive charge. And so what the battery is doing is just kind of pumping them around from negative to positive. And so this is the charge difference that occurs, plus on the right, minus on the left. And now, if we're doing our loop rule in the direction of the current, so clockwise, going across the capacitor, we're going from positive to negative. Right? So we're going from positive to negative, which is a negative voltage drop. Right? So that's how we know the voltage change across the capacitor in this case is negative, because following the current is crossing from the negative side to the positive side. The current isn't actually crossing this gap, right? There's nothing jumping across here. But the loop rule is we're really taking points in space, right? We're just saying, what's the difference between this point and this point? And it's Q over C. So anyway, there's that. And then finally, we reach the resistor, where it works the same, minus IR, whatever current we have. And that's our loop. So we've just added a term into our loop rule. So this is just kind of some random time. Let's take a look at our evolution over time. So let's start at t equals 0 with an uncharged capacitor. So right now, before anything has happened, these are just metal plates, nothing special about them, an empty capacitor. And so if Q is 0, then delta V across our capacitor is 0, right? There's no voltage difference between two empty metal plates. And so our loop rule looks just like it would if we just had a battery and a resistor. And so we can find whatever the initial current is here. Great, this looks just like what it did before. Now let's let a little time pass. So as time passes, as we decided, current is going to get pumped around. Positive charges are going to leave this side, wind up on this side, and we'll get some buildup of charge. And so now Q is not 0, and neither is delta V across the capacitor. So now we have this term here. And if we introduce this minus Q over C term, so this Q over C term grows. What has to happen to our minus IR term? It has to shrink, right? Because this equation still has to work out. And so this is kind of, everything's working together, because we know as the capacitor builds up in charge, it becomes harder and harder to do so, which we said means the current is going to decrease, right? As it becomes harder, less current is going to flow, and this equation supports that. Where as Q grows, I has to shrink, because C and R, those are just constants. Those are just characteristics of the resistor and the capacitor. So at this kind of midpoint, we have some charge built up. There's still current flowing, but less than we started with. And then finally, if we let a lot of time pass, much greater than whatever tau, the time constant, is for this circuit, which we haven't discussed explicitly yet, but it's exponential change, so we know we have one. After a lot of time has passed, our capacitor fills up completely to a point where Q over C is exactly equal to epsilon. In other words, the capacitor charges up to the same voltage, equal and opposite voltage, as the battery. And so now there's no more current flowing, because if there was current flowing, the charge would be increasing here, which we know it's not. And so the resistor is now doing nothing. There's no current flowing through it. We just have a capacitor here. This voltage change probably should be minus epsilon if we're going in the direction that current used to flow, but it's charged up to the voltage of the battery, which kind of makes sense, right? Like, how much charge or how much voltage can I put on this capacitor? Well, however much I have from the battery. Just like with the fluid analogy, the height difference, the maximum height difference that you can reach, is just determined by how strong your pump is. Okay, so now we've talked about capacitors kind of qualitatively, seeing how they work. Let's connect them to the exponential functions that we made before. So first I want to make one for Q, the charge on the capacitor. I'm saying it's changing exponentially. Everything that's changing is changing exponentially here, exponential decay-wise. Is Q increasing or decreasing over time? The charge on this capacitor? Increasing, yeah. It starts at 0 and reaches some maximum. So that tells us we want the version of exponential decay that increases, right, and asymptotically approaches a maximum. So that's going to be this version of it, right? So we know Q is equal to Q naught times 1 minus e to the negative t over tau. And it's I'd say simple, but like that's really the way we're going to decide when we're writing these out which version of the equation to use. Is this thing increasing or decreasing? And that tells you which version you should have. So since Q is increasing, we need this version, and it obeys if we start at time t equals 0, we get Q equals 0, because you get 1 minus e to the 0, so 1 minus 1. And so, yeah, and it connects the same way. A, there's no charge. B, some time has passed, maybe one time constant, so maybe tau has passed. And so our charge is growing up. Here it looks like half, but we know it shouldn't exactly be half. And then C is sometime way in the future. Current has stopped flowing, and we're at equilibrium, or roughly at equilibrium, much later on. So Q increases, sure, but the rate of change of Q is decreasing, right? The slope is becoming more and more shallow as we get toward equilibrium, and it becomes harder to pump more and more charge on the plate. All right, so now let's try to do this for current. Is current increasing or decreasing? It's decreasing, because we have some initial current. That's what causes the charge to build up, and then the charge reaches a maximum, and no more current can flow. So we've kind of just discovered here how current and charge are related, which we already knew. What are the units of current? It's charge per second. It's just the flow of charge. Actually, it's the rate of change of charge, too. Charge per second, delta Q over delta T. You'll explore some of this like kind of calculus leaning stuff in DL. But anyway, I is decreasing, right? And so we have some maximum current that we start off with. That's part A. Then some charge builds up. It becomes difficult to add more, but it's still coming on to the capacitor. And so our current is significantly decreased after one time constant, but it's not 0 yet. And then after a lot of time, we have maximum charge on here. No more current can flow, or roughly no more, and we are close to equilibrium. And this follows the shorter decreasing exponential decay. So I think that's a good mental way to think about it, that all of this is exponential decay. Again, decay refers to the decay of the rate of change, but we have an increasing exponential decay and a decreasing exponential decay, but they're all decay. Okay, so why don't we do a little test of this here. So in front of us I have this exact circuit, really. I have a battery hooked up to a resistor and a capacitor. And the capacitor is uncharged. So these things here are voltmeters. They tell us the voltage across each of these. And so I'm going to turn my battery on. Nothing's going to happen yet because there's a switch here, so I have to push down here to actually close the circuit. So I'm going to close this circuit, and what do we expect? Which of these do we expect to initially have a higher voltage change, a larger voltage change? Well, what determines the voltage change across the capacitor? We just took a quiz on this. It's minus IR, right? So the current times the resistance. So we know that the current is going to be largest at first because the capacitor is empty, so it's very easy to pump current through. So we're going to have a large current, a large voltage drop across here. What determines the voltage drop across the capacitor is the charge, right? And so initially the charge on it is 0, and so our voltage is 0. And so we should have voltage change here going from 0 and increasing, and voltage change here going from a large value and then decreasing as the current goes away, which kind of makes sense, right? So here, I don't know if you can read it, but this says 5. So this is a 5-volt power source. So this is like a 5-volt battery. And going to our loop rule, so let me go back to that. If we look at let me look at the complete one. Our complete loop rule here, we have to still obey the laws of our loop rule here, that as we go through the loop, we have to get back to 0 if we complete a whole loop. So if I gain epsilon volts and then have a voltage drop across the capacitor and a voltage drop across the resistor, I have to add up to negative 5 volts, right, to get back to 0. And so the sum of these two voltages should equal, at least in magnitude, the voltage of this. So I say all that. It's going to happen too fast for us to see, and they're not super accurate. So, well, let's just do it and see what happens. So I'm going to close the circuit. So right away, you see the resistor voltage was huge, right? Our maximum amount of current that can go, voltage across the resistor. And then as time passes, the voltage across the resistor starts to shrink because the current is decreasing, right? It's becoming harder and harder to put more charge on here. And so the current is going down until eventually no current is going to flow through here. So now let me reset real quick. So now the voltage on the capacitor is back to 0. And voltage across the resistor is back to 0 as well. So now we know what happens to the resistor is that we have a maximum voltage across it, and then as I goes away, the voltage difference across here goes to 0. Now let's pay more attention to the capacitor, where we have 0 volts across it because there's no charge on it. And now I'm going to close the circuit, and now instantly charge starts building up. And so as Q increases, the delta V across the capacitor increases, and we can see that now as it increases, it's slowing down. So it shot from 0 up to 1 really quickly, and now as it gets toward 4 and 5, now it's just creeping ever so slowly. Why? Well, the charge on the capacitor, the rate of change of the charge building up, is just the current. So if the current's going down, the rate of change of the charge is also going down. Okay, so now a fun thing. I'm going to open the circuit, and it's actually going to leak very slowly because this is like an imperfect setup. But if you notice, the voltage across the resistor goes to 0 because I disconnected the circuit. There's no more current. But the voltage across the capacitor actually doesn't change, or roughly doesn't change. Some charge is leaking away. But that's because, if you look at this circuit, if I charge up the capacitor, I guess this one's good. If I charge up the capacitor and then cut the wire, there's nowhere for this charge to go. Right now it's just stuck there. It wants to leave, but unless I connect the circuit back, then there's no way for these positive charges to get back onto this plate and cancel them out. So they're just going to stay. And that's why the voltage across this capacitor stays relatively constant. Here, let me charge it back up. So we can actually analyze that, the process of the charges going back together when we connect it back together. And what we're going to do is actually remove the battery and then just connect the capacitor across the resistor. So when it was the battery and the capacitor, the reason the charge built up is because the battery was there. It forced charge one way to the other. But the charge doesn't want to be here, right? It's only here because the battery's pushing it there. If we remove the battery and close the circuit just with the resistor, this charge doesn't want to be here, and now it has a clear way to get back to the other side. And so it's actually going to discharge. So now we've closed the circuit with just the capacitor and the resistor, and so these positive charges are going to say, great, now I have a way home, and the current is going to reverse from where it did before, flow back across the resistor, and cancel out until it reaches equilibrium, which is 0 charge on each plate. And so we can also see our loop rule here, where now starting off, we have like Q max over C, so whatever this maximum charge that was built up on the capacitor. Let me charge it up one more time. Maximum charge I build up on the capacitor. And then over time, Q is going to decrease, right? As the charge leaves, Q goes down, and so the voltage drop across the capacitor goes down, which tells us also that the current is going to decrease, right? As less charge leaves, then less current, then you just get less current. Another way to think of it is as some charge leaves, that frees up space on the capacitor, and so the charges aren't in as big of a hurry to leave because there's not as much repulsive force on them. And so they don't leave as quickly. So we still get this exponential decay behavior toward the equilibrium that is an empty capacitor. So now I've charged up the capacitor, and what I'm going to do now is just connect the capacitor across the resistor, and as we'll see, initially we get a big current across the resistor, and the voltage across the capacitor starts to shrink. And now the charges are just leaving the capacitor across the resistor and canceling out. The current is going down to 0, so the voltage across the resistor is going down to 0, and the charge difference is going down to 0, and so the voltage across the capacitor is also going down to 0. And so we get an exponential decay behavior as well. At some time later, Q is decreased, I is decreased, and then finally Q goes to 0, and so I also must equal to 0. And that all really comes from the loop rule. And so we get this interesting thing. Here I've just plotted the voltage across the resistor and the capacitor at the same time or on the same plot. And you see now the voltage across the capacitor is positive, but the voltage across the resistor is negative. And this chart here really kind of shows us the loop rule, right? It tells us that at any point, the sum of the voltage changes across the resistor and the capacitor have to equal 0. And if you take a look here, minus QC plus QC, and they just follow like this kind of flipped version where at the end, they're both equal to 0. So this exact math you'll follow a little more in DL, but this is where we're headed. Some other things to note: when you have a system like this, you're going to work out what the time constant is in terms of these values, but the time constant ends up only depending on R and C, so the resistance and the capacitance. They're just like the constants related to the circuit, and so the speed at which the circuit evolves depends on the size of the capacitor and the size of the resistor. You'll also play around a lot more with the mechanics of the time constant. So there's some cool behavior about that and the half-life that you'll uncover. But yeah, I would say really these are good DLs to show up prepared for. I mean, every DL is a good DL to show up prepared for. But I would highly recommend doing some review of either this lecture or some YouTube video, whatever you need to do so that exponentials are a little bit fresh when you're going in. Because I think the learning that you do, the hands-on learning, is really important, especially because next lecture we're just going to leave this stuff behind, and it will show up on the final. So, yeah. Have a good rest of your week.